I would like to welcome each one of you to the spring quarter ENR 5268. That's a soil and climate. I regret that we couldn't meet in person today because of the bad weather, but hopefully we will have in-person lecture on Tuesday. As I have mentioned in my written message to you, we would also like each one of you to give me the title of your seminar that you would like to present. One presenter every Wednesday, and also give the preferred date of preference. Those who might present Wednesday will get some bonus point. I think that may be a good starting point. So the lecture today is history of climate change. And we can take from the geological records, information, books. When did the Big Bang happen? 10 to 15 giga year ago. Then solar system evolved about 4.5 to 4.6 year ago. Formation of the solid crust of the earth about 4 giga year. And then 3.5 billion years ago, oxygen-free atmosphere, which primarily had methane, ammonia, water, carbon dioxide, nitrogen, sulfur metabolizing cells, and these kind of things. Then origin of life and chloroplasts and use of chlorophyll in photosynthetic plant started about 3 giga year ago. About 2.5 giga year ago, sedimentary rocks formed, and concentration in the atmosphere, oxygen began. Oxygen was created, of course, by plant that photosynthesized. More complex bacterial life evolved in response to the oxygen-rich environment. But 1 giga year ago, origin of the blue-green algae, start of the photosynthesis, formation of oxygen, and then 0.7 giga year ago, the emergence of multicellular organism, and 0.6 giga year formation of ozone screen and origin of life on land. And therefore, the climate evolution, atmospheric evolution on the Earth began. And we can indicate the era. Again, geological books will tell you atmosphere about 4.6 years ago had primarily hydrogen, helium, methane, ammonia, water vapor, carbon dioxide. Earth crust was molten magma. And the Archean year, 2.5 giga year, nitrogen concentration was 75%, carbon dioxide 15%. We had carbon monoxide, methane, ammonia. Solid crust was formed and formation of ocean and carbonates happened. During the Proterozoic period, 2.5 to 0.5 giga year ago, nitrogen was 70%, carbon dioxide 10 to 30%, oxygen 2 to 10%, and ozone was in the stratosphere. We had molecular life, anaerobic microbial life, methanogen, sulfate-reducing bacteria. You notice CO2 concentration was 10 to 30% compared with current about 0.042 or 0.043%. And oxygen concentration presently about 21% compared with 2 to 10% at that time. During the Phanerozoic period, the atmosphere eventually evolved. At present, I'm looking at the last column, nitrogen is 78%, oxygen 21%, carbon dioxide 0.043%. Because the plants and life evolved and plants photosynthesize and convert CO2 into carbohydrates and release oxygen in the atmosphere. So this is where we have pre-industrial era more closely, when the carbon dioxide concentration was about 0.028%, and now we have 0.043%, and it is increasing at the rate of 2 parts per million per year, leading to the so-called global warming. So now let's look at, however, some of the closer other planet are compared with Earth. As you have seen, Earth is 78% in atmosphere nitrogen, oxygen is 20.9%, CO2 is 0.04%, and gravity is 1, and the atmosphere pressure is 1.013 bar. You can convert bar to kilopascal and other units. Now compare that with Venus. Carbon dioxide is 96%, nitrogen 3.5%, and other gases 0.5%, atmospheric pressure 93 bar, compared with 1 bar at the planet Earth. Therefore, it has a temperature of 461 degrees centigrade. This is the extreme case of greenhouse effect. Carbon dioxide, 96%. And if we look at Mars, we have carbon dioxide, the same 95%. Nitrogen is about 2.7%, but atmosphere is only 6 millibar compared to 93 bar in Venus. Therefore, Mars has a temperature of minus 46 degrees centigrade. So you've got 3 planets, Earth, Venus, and Mars. Venus, average temperature minus 46. Venus 10 times that, 461 degree plus, more than 10 times positive point of view, and Earth 15 degrees centigrade average temperature. So if there was any heaven amongst these planetary systems, I think the Earth is the only one. Therefore, we should take care to protect its life support processes. And that brings to the statement from Carl Sagan, who wanted to say that what I just said, protect the Earth, but much better than I could, because he said, look again at the blue pearl in the space. That's here, that's home, that's us. On it is everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregates of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, every hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every super leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. And that's the planet Earth. Unique planet in the solar system. We do not know if there is anything like this elsewhere, but in our solar system, this is it. And this planet, if you look at the history on x-axis from 18,000 BC to now, the current era, 2040, 2024, we got temperature plotted on y-axis, and it looks like changing over time until we reach about 10,000 BC, when the temperature became more or less constant. And at that point in time, several things happened because of that long summer that we had. Not like what we got today, but on the average annual temperature. And this is where the agriculture began. About 8,000 BC, when the temperature had stabilized, the CO2 concentration was favorable, the temperature was kind in northern hemisphere during the summer and springtime, and therefore the agriculture was made possible. And in 1760, then the Industrial Revolution came. The question is, what did the so-called Anthropocene began? Did Anthropocene begin in 1750 with the onset of Industrial Revolution, as many people have said, including Paul Crutzen? Or did Anthropocene begin actually with 8000 BC when we invented the agriculture? And that's a question of debate. I personally think, from my point of view, when the agriculture began about 10,000 years ago, that's when we started to transform surface of the earth by deforestation, by biomass burning, by draining the wetlands, by cultivating the land to agricultural seasonal plants that caused erosion, that decreased the organic carbon content. I think that's when the Anthropocene and its impact actually began. But Paul Crutzen stated that Anthropocene began at 1750. I think at 1750, the Anthropocene got accelerated. Its impact got accentuated, that it actually began. But I'd like to hear your views. What do you think? When did the Anthropocene begin? The human impact since 8000 BC was kind of slight and modest and slow, and it was linear, going up to about 8000 BC to Industrial Revolution. Since the Industrial Revolution, as I said, it began to increase drastically. And this hockey stick kind of diagram, that's where Paul Crutzen said, I call, because of the changes caused by population, energy use, water use, deforestation, carbon dioxide emission, land degradation, desertification, fossil fuel combustion. Therefore, Paul Crutzen said, and by the way, Paul Crutzen was a climatic chemist, originally from Holland, but working at a place in Germany. Claude Lawrence and I had an honor to work with him for 2-3 years. In fact, we have published an article with him. He called this era from 1750 to now Anthropocene. I had the honor to discuss with him and state, no, I think Anthropocene actually began here. And of course, he listened, but it was not easy to convince a person of his scientific caliber. Considering that, the question that we want to discuss in the class are, what are the global issues of the 21st century that we are facing today? Well, the first global issue is the population. That's the driver of the other issues. And the population present is 8.2 billion in 2025 January. And it's increasing at the rate of 1.14% on a global scale per year. And that comes to 93 million per year more people. Divide that by 12. That's roughly 8 million more per year new mouth to be fed. And I should state that there is also those mouths to be fed also have a brain, so that they can become innovator and addressing the problem that we are going to face. And some of those problems are created by us, but we need to also address them. So number 2 thing, the per capita arable land area, which at present is about 0.19 hectare. What I've done is taken the global per capita land area and divided by 8.2 billion. That's what you had. But as the population will keep increasing by 2025, which is now, the per capita arable land area, which we had about several decades ago, will decrease less than 0.07 hectare for 30 out of 200 countries of the world. 30 countries, people will have per capita arable land area this year of less than 0.07 hectare. Some of them in South Asia, very large population, not only just South Asia, of course, East and North Asia, the same thing, very large population, but arable land area small and decreasing, but population increasing. Therefore, per capita arable land area keeps decreasing. Soil degradation affects 40 to 50% of ice-free and desert-free land, 40 to 50%. And the area under degradation processes erosion, cellularization, elemental imbalance, acidification, many other processes, estimated about 5 to 10 million hectare per year. Number 4, renewable freshwater supply, which we need about 1,000 cubic meter per person per year on average for 30 countries. And now, and 58 countries, about 4 billion people by 2050, will face severe water shortage, water scarcity, drought, and other problems that are caused by low water supply. The CO2 concentration, some of you may like to check by Google. I think today is about 427 part per million. Remember, it was 280 part per million pre-industrial era. And you know how to convert part per million to percent. Divide by million, multiply by 100, that will be percent. So it'll be 0.043%. And increasing 0.5% per year, which is equal to about 2 parts per million per year. So next year, 429, and next year, 431, and up it goes. Therefore, the risks of global warming and uncertain climate, extreme events like one we had today, will their frequency increase over time. Energy use, which is a fossil fuel source, we were consuming about 565 quads, and quads is 10 to the 15 BTU, and increasing at the rate of about 2.2% per year between 2001 and 2025, and it will probably continue increasing at the same rate or even more if the alternative to fossil fuel are not found in the current years. Per capita grain consumption, total grain produced by the population is about 300 kilogram per year. In some cases, it's increasing. But globally on the whole, it may be decreasing. In some isolated area or few countries, it may be increasing, but globally there is a chance of decreasing more. That means food insecurity. That means malnourishment. And food insecure population at present is about 733 million, and that's an underestimate. Why is it an underestimate? Because the refugees by war in Eastern Europe, war in Middle East, war in many other parts of the world, these wars are causing increase of refugees, both in their own country that's internally displaced, as well as external refugees. Therefore, the actual population affected by food insecurity may be much higher. Some people think it's 1 billion people, but the records indicate that 733 million. Per capita CO2 emission in the world is about 5 metric ton, that's megagram, of CO2 equivalent per year. And in the US is about 18. And in some countries of the Middle East, it's about 50 to 100 megagram per year per capita, because they burn more in those harsh environments to keep their environment cool and pleasant. And humanity's water footprint at global level, it's 1358 cubic meter per year, and it's increasing. That means the amount of water we use, just like land footprint and carbon footprint, water footprint, because it's a fresh water supply, is really very limited resource. Now, when you are asked a question, what are the global issues? You may have another list, and I'd like to see that. And maybe your list is better than what I have shared with you. So it'd be very interesting to hear what you come up with a question of the global issues from your perspective. One of the problems is Sustainable Development Goals, which is the UN Agenda 2030. And these goals were developed in 2015. The idea was to achieve hunger-free world by 2030 and no poverty by 2030 and strong climate action by 2030. I think those good goals, very nice goals, but they're not on track. They're not going to be accomplished by 2030. I said 733 million people hungry. Will by 2030 there be zero hunger? That's what the goal says. Will it happen? It says no poverty by 2030. Will that be right? Will that happen? Really not. But it's a good goal, something goal to try. So think what you think of the issue. The driver of climate change is population and the lifestyle. And if you see the plot of graph of time from 1860, 1880 to 2200, and you plot the CO2 concentration in the atmosphere, they are exactly the same. So population is driving the CO2 concentration, and CO2 concentration is driving the climate change. Therefore, we can decide some of the human systems that are evolved in the Paleolithic period, so-called Homo erectus tribes, hunter-gatherers, stone and fire were the tools. That was 2.5 million years ago. Population was only 2 to 20 million people. Then we came to Neolithic period, Homo sapiens, agriculture was evolved, powerful tools were developed. Era was about 0.01 million year ago. Population was 900 million. Then we have carbon civilization. And that is what name I have suggested and suggesting. You may not agree with it. There are many others who do not agree with it. But I wrote an article in 2007 when I was president of the Soil Science Society of America. And the article was, "We are in the carbon civilization." And the question is, did Stone Age end because we ran out of stones? No. So I think carbon civilization will probably also end long before we run out of fossil fuel carbon. And that the population of this era is going from 7.3 to recent estimate is that it probably will equilibrate, get type total maximum to 10.8 billion by 2080. 10.8 billion. That will be a great thing if we can do it. As a force in transforming the biosphere, so humans are really a big force in transformation of the biosphere. So what is the greenhouse effect then? You have solar radiation, you have glass structure, greenhouse. I got outside where I am. In fact, I'm looking at the window, the greenhouse on my left-hand side. And what we got, a glass structure and plants inside. So what's happening is the long-wave radiation cannot leave the greenhouse. Short-wave radiation can come in. Once you see 0.1 to 0.4 micrometer ultraviolet radiation from the sun, but the long-wave radiation emitted by the Earth cannot escape 5 to 15 micrometer. And some of it is returned back by glass to enter the glass enclosure. Therefore, the temperature of the enclosed area is much greater than the temperature outside. And you feel it when you walk through a greenhouse, especially during summer or in winter. You are outside and go inside the greenhouse, you see the difference between the temperature of the two environment. And this is called the greenhouse effect. Thermal radiation from inside a greenhouse cannot escape. Therefore, it's called a greenhouse effect. Now, we think atmosphere has the same process. You got sun, you got the planet. Planet has the atmosphere, the green, surrounding it. The ultraviolet radiation comes in. It penetrates the atmosphere, but then the atmosphere does not permit the long wave radiation to escape, and some of it is returned back to the planet. Therefore, the planet is warmer than it would have been if there were no greenhouse gases. And these greenhouse gases, which are the property the same as the glass in a glass house, they are symmetric molecules, like water molecule, HOH. One O in the middle and two H. One C in the middle and two O, carbon dioxide. one N in the middle, pardon me, one O in the middle and two N on this side, N2O. CH4, two H and C in the middle, natural gas methane. These are symmetric molecules. If you take oxygen or nitrogen or hydrogen, OO, NN, HH, they are not symmetrical. Therefore, they do not have these properties. So these symmetric molecules have the property to act as the glass does in a greenhouse. Therefore, the Earth is warmer with the natural greenhouse effect than it is without it. And this greenhouse effect is being accentuated, increased by human activities, such as fossil fuel combustion, such as deforestation, such as biomass burning, or draining of wetland, plowing of the land, erosion of the land, which lead to emission of different gases, some of those which I mentioned here, CO2, N2O, CH4, into the atmosphere. These are the symmetric molecules which vibrate as the long wave radiation hits the bond, and that vibration absorbs the energy, and that's the greenhouse effect. There's a difference between the haze and the greenhouse effect. The haze effect, there is no retention. In a greenhouse effect, there is a retention of the energy back, and that's the difference between the two. Historically, in 1783, volcanic fog caused by eruption in Iceland was attributed to the compounds in the atmosphere emitted through eruption. Joseph Fourier in 1850, a Swedish scientist, he did the energy balance of the Earth and actually defined the so-called greenhouse effect. John Tyndall in 1859 indicated that not all gases are transparent to heat. Therefore, water, methane, and carbon dioxide can absorb heat. In 1896, Svante Arrhenius suggested the effect of CO2 on global temperature. Hogbaum, he gave the biogeochemical cycle of CO2. By the way, Svante Arrhenius, coming from Sweden and Nordic countries, calculated how much coal has to be burnt to keep the winter warmer and spring more pleasant than it is in the Nordic countries. His goal was, how can we warm up the Earth? He did not realize that another 100 years from that time, we'll be thinking about cooling it rather than warming it. Chamberlain proposed a model of carbon exchange, including the feedback. Some processes have feedback. The aerial ocean was described by Arthur Wallace. Guy Stewart Callender calculated the warming effect of CO2. Roger Revelle, who was president of the US National Academy in the 80s, mid-80s, 1980s. And I had the honor to host his visit to IIT in Nigeria and learned many things from him. National Academy then asked me to accompany him to China and to India and Sri Lanka, not China, India and Sri Lanka. And I realized that I was very fortunate and privileged to travel with the world scientist at that time, most pioneering scientist in climate change that I would ever meet. The Gaia hypothesis, Jim Lovelock, I also had the honor to meet him. He wrote that the Earth behaves like one living organism. His book, The Gaia, indicates Earth is one living organism. IPCC was initiated in 1988. In 1992, the UNFCCC, the Climate Summit, that we know now being held every year. Kyoto Protocol was signed in one of those in Tokyo in 97. 2015, COP21 Paris suggested the program called 4 per 1,000, putting carbon in soil of the world at 4 per 1,000, 0.4% per year. And Minister of Agriculture and Forestry, Stephen LaFolle, visited Ohio State to discuss this suggestion with us here. In 23, soil health was cited for the first time at the IPCC meeting in Saudi Arabia, where the meeting, UAE, where the meeting was held. And then 24, the meeting was in Baku. And there they proposed agriculture and land-based sink as a part of the solution. So from 2015 onward, there has been a significant emphasis on land management, soil management, and agricultural practices as a possible part of the solution to climate change, adaptation, and mitigation, which I think is a good idea. Then we realize that food system, which are so important to humanity, but they can't live without food. Nobody can live without food. Therefore, they can be produced in such a way that rather than being a problem, they can be a solution. And that's a very important concept. And since 2015, that has been given a very significant emphasis. Some of these points I've already discussed: the volcanic fog of 1783, the Joseph Fourier doing the heat balance, John Tyndall talking about rivers leading to atmospheric rivers, leading to change of the water balance, carbonic acid in the air by Svante Arrhenius. He calculated the mean alteration of temperature that would follow if the quantity of carbonic acid varied, so that this winter and spring in Scandinavian countries could be warmer. But his arithmetic, done mostly manually, was outstanding. Arrhenius estimated that cutting the amount of CO2 in the air by half would cool the world by maybe 5 degrees centigrade, and that doubling the CO2 would raise the temperature by 5 to 6 degrees centigrade. Now, he was talking about 1900, when the concentration was about 280 to 290 parts per million. So doubling means 560 to 600 parts per million. Arvid Hogbaum, 1897, did the calculation of the temperature in the Arctic region would rise about 8 to 9 degrees centigrade if the carbonic acid increased 2.5 or 3 times its present level, and the world present production of coal reaches in round number 500 millions of tons per annum, or 1 ton per square kilometer of Earth's surface. So these calculations began about 1900. Aerial ocean and climate, you have heard about aerial rivers. Alfred Russel Wallace, he estimated that the great aerial ocean which surrounds us has the wonderful property of allowing the heat waves, heat rays from the sun to pass through it without its being warmed by them. But when the earth is heated, the air gets warmed by contact with it, and also to a considerable extent by the heat radiated from the warm earth. Because although pure dry air allows such dark heat rays to pass freely, yet the aqueous vapor and carbonic acid in the air intercepts and absorb them. So the greenhouse effect was very well described by 1900 by many scientists, including Arthur Wallace. He also indicated that the storms are so violent that no human structure can resist them, while the largest and most vigorous trees are torn to pieces or overturned by them. If our atmosphere received a somewhat greater amount of sun heat, these tempests might be so increased in frequency and violence as to render considerable portion of the globe uninhabitable. So in 1903, Arthur Wallace was warning the world what extreme events can do if the CO2 concentration in the atmosphere would keep going up by the so-called anthropogenic activities, mostly fossil fuel combustion and deforestation. Calendar in 1938 to the Royal Meteorological Society argued that numbers indeed show global warming, and it's us, human industry, which is responsible. So that was known by 1940. Time magazine, January 2, 1939, had a special issue indicating that the world was already warming. This is what the Time magazine said. Gaffers who claim that winters were harder when they were boys are quite right. Whether men have no doubt that the world, at least for the time being, is growing warmer. And that was 1940. Then the recent Time magazine, uh, which indicates be worried because global warming, that's 2006, that global warming is really very serious point and reaching a tipping point. The polar caps are melting. This is 2006. Polar ice caps are melting faster than ever. More and more land is being devastated by drought. Rising waters are drowning low-lying communities. By any measure, the earth is at the tipping point. That was Time magazine, 3rd of April, 2006. The prevailing scientific view on climate change, therefore, is without big changes in emission rates, global warming from the buildup of greenhouse gases is likely to lead to substantial and largely irreversible transformation of climate, ecosystem, and coastlines later this century. So we are talking about very serious problems if the global emissions continue at that rate. And the US-China reached climate accord after months of talks. That was a great sign. But its implementation, as you can guess, has not really happened. This was Obama's period. You can see him and his Secretary of Agriculture. The Gaia hypothesis needs some attention. Jim Lovelock, as I mentioned, his book Gaia, and we had a meeting organized in his honor by people in Brazil, and he gave a very good lecture. This must be in about mid-80s, 1984, 85. And he wrote in his book, Gaia, what makes global warming so serious and so urgent is that the great Earth system, Gaia, is trapped in a vicious circle of positive feedback. Extra heat from any source, whether from greenhouse gases, the disappearance of the Arctic ice, or the Amazon forest, is amplified, and its effects are more than additive. It's almost as if we had lit a fire to keep warm and failed to notice, as we piled on the fuel, that the fire was out of control and the furniture had ignited. When that happens, little time is left to put out the fire. Global warming, like a fire, is accelerating, and almost no time is left to act. That was Jim Lovelock in 1979. And I think this is where I said I had the honor to meet him. And of course, Paul Crutzen, who was there at that time. Paul Crutzen got Nobel Prize, but not Jim Lovelock. The greenhouse effect then is a biogeochemical process. The greenhouse effect is a biogeochemical process that is essential to the evolution of life on Earth as we know it. And this greenhouse effect has raised the average temperature at the surface of the Earth from minus 18 degrees centigrade to 15 degrees centigrade. If there was no greenhouse effect, the temperature of the Earth would have been minus 18. Remember minus 46 for the Venus? Earth would have been minus 18. But because of the greenhouse effect, it's 15 degrees. Therefore, the natural greenhouse effect is 33 degrees centigrade. That's before anthropogenic change, before the Anthropocene. And above that, it would otherwise have been negative minus 18, but it's now 15. The greenhouse effect has allowed liquid water to remain stable and provided the fundamental substrate for biological activity and life as we know it. So greenhouse effect is very, very essential. So what's the problem that we are talking about? We are not talking about greenhouse effect. That is essential to life. We are talking about global warming. Now that is something else. Therefore, what is global warming? It's the acceleration of the greenhouse effect, leading to increase in global temperature at a rate greater than 0.1 degrees centigrade per decade, such that the ecosystem cannot adjust to this rapid change. So please understand the difference between the natural greenhouse effect and the global warming. Global warming is the acceleration of the natural greenhouse effect by anthropogenic activity that began with the Anthropocene, which might have begun with the onset of agriculture 10,000 years ago. According to Paul Crutzen, only since the Industrial Revolution of 1750 when the Anthropocene began. Maybe you have a completely different opinion, but that's global warming. So we are concerned about global warming, not by greenhouse effect. Greenhouse effect and the biosphere have very closely interdependent. For each 1 degree centigrade increase in global temperature, the vegetational zone, remember this tropical forest, and then we have the temperate climate, and then we have the Arctic climate. Those zones, the climatic zone, with each 1 degree centigrade can shift poleward, even the northern hemisphere north and the southern hemisphere south, at the rate of 200 to 300 kilometers for each 1 degree centigrade increase in temperature. Current climate change, some people think it's about 1 degree centigrade already. This slide needs to be updated. The current value close to 0.9 to 1 degree centigrade. The rate of increase is more than 0.2 degrees centigrade per decade. Sea level rise is about 0.1 to 0.2 meters since 20th century. Precipitation is changing and extreme events are changing. And if you look at the CO2 curve, in 2016 it was 402 parts per million. Today it's 427 parts per million. And these curves go up and down depending on whether you're in the northern or southern hemisphere, and that's called the Keeling curve. We will have some more discussion about the Keeling curve. If I look at closely one of these, it goes up and down. In the northern hemisphere, CO2 concentration highest in winter, this time of the year, because the plants are not growing. Therefore, there is more CO2 in the atmosphere. And the southern hemisphere is just the opposite. That's what that up and down looks like. But the difference between climate and weather, climate is what you expect, long-term, average. And weather is what you get, which changes very rapidly. Day to day it changes. So climate is the long-term average, and weather is like rolling the dice, and climate is like loading the dice. We have two types of temperature scale, Fahrenheit and Celsius. And I think we use, of course, Fahrenheit temperature scale in this country. Everywhere else it uses Celsius. It's a good idea to use really Celsius. Scientifically speaking, it's a Celsius scale. Sea level rise is happening very rapidly. Right now, it is already about 0.5 meter since the Anthropocene. So humankind has really influenced the environment. Mankind is on the horns of a dilemma. For whether we like it or not, our collective way of life has become unsustainable, and we need to do something about it, and soon. The choices we have already made about the way we lead our lives have been slowly eating away at the very support system that enables us to live and breathe. This cannot and should not go on. We need to make some tough decisions. We need to make them now, and we need to act on them as one with total and undivided commitment today and in the future. Why? Because we have only one planet Earth. And as I talked to you before, there is no other planet like this in our solar system. This is our home, and only one home we have. Therefore, we cannot destroy it. Faced with the facts we cannot argue against, we need to consider some critical priorities and accept that we have to make certain sacrifices. We need to start putting life ahead of lifestyle. That was IMO World Maritime Day. And that was the summary of the introductory lecture I had planned to present to you in person. I will like you to hopefully get a chance to review it. The link to this lecture will be available online today in the afternoon. And I would like to receive your suggestion who might want to present on Wednesday on any topic that I have presented today or what you that might suggest. And if you do not volunteer anyone, that's okay. I will present something else on Wednesday initially and then have discussion amongst you. But from the next week onward, the week of 13th of January, or every Wednesday, we must have one of you make a presentation. Sometime it may be two of you making that presentation. With that, I thank you for enrolling in this class. There's a room for more of your colleagues and friends to enroll in this class. We normally have about 30 students. Total enrollment at present is about 22, 23. So we have a chance. We do not have any exams. Most of it is for homework. I will give 2 or 3 and Dr. Barry Lyon will give 2 or 3. And Dr. Barry Lyon, in my opinion, is one of the best professors at the Ohio State. And you will hear from him on the long-term carbon cycle. You will hear from me on the short-term carbon cycle. And management of short-term is more easier and more practical than that of the long-term carbon cycle. Combined together is the combination of lecture on this very course. Have a very good day and look forward to seeing you on Wednesday. Thank you so much.